Welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we will be looking at section 1.3, which finishes up our first chapter in chemistry. And what we're going to be looking at section 1.3 is really thinking like a scientist. Now, what we're going to be looking at in this section is the scientific method, which is something for years you've been talking about. You look at scientific method in elementary school, you look at middle school, and it really is the basis for all problem solving in science. And there's many ways to depict it, but this is one I kind of like because it shows basically the cyclic nature of things. When you are going from your hypothesis to your experiment, you're basically doing a series of experiments and you keep looking at things and coming to conclusions and revisiting your hypothesis until you have what you believe is to be true. And then it moves on to the theory and so forth. So this does a nice job of looking at, the different parts of our process here. Now, scientific method is actually a systematic approach of problem solving. So it's a very systematic, organized way of looking at and studying problems in the world around us. So that's really what we're doing, is trying to have a better understanding of what and why things are happening around us. Now, it starts with observation. So you make some type of observation, collect some rudimentary data about something, and then in your head you start to piece together what's going on. And that gives you your hypothesis. So we go from our observation to our hypothesis, our tentative explanation about what's going on. Now, we could be describing why, or we could be just saying what, but we're trying to organize and look for trends and patterns in our observations to come up with what we think is going on. Then from there, we devise experiments to test that tentative guess, that hypothesis. So we look at some very controlled situations for testing, is what we believe to be true actually going on? So we basically put our hypothesis to the test. Now, at that point, sometimes we find out, well, no, under looking at it under very controlled situations and collecting more data, our hypothesis was wrong. And at that point, we have to go back to our hypothesis and start all over again. And that's part of the cyclic nature of this process. Now, if our experiments seem to uphold the hypothesis and make it look like our hypothesis might be correct, under extensive testing, eventually an experiment becomes a conclusion. And there's two different types of conclusions, theories and laws. They're both valid. They're both based upon observation. They're both the end result of, a lot of experimentation. The difference is really how we're looking at it. Theories and laws are different types of conclusions. And depending on what we were looking at in our experiment and what our hypothesis was, we might end up with a theory or a law at this point. And you have to understand, at that point, our conclusion is tested forever. We've done some extensive testing, and this is what we think is going on. But every other person who looks at it is, in essence, testing and experimenting again and again and again. So that conclusion gets tested forever. So the experiment conclusion process gets tested forever. And at some points, some of our conclusions that through the instrumentation and beliefs of a certain period of time, eventually with new instruments get overturned and we realize, no, that wasn't what was happening. So you need to understand, conclusions aren't true. We just believe them to be true because they've been extensively tested. And what conclusions really are things that haven't been proven wrong. Because through our experimental process, all we can really do is prove something is invalid. We don't really prove it's true. What we do is we say, I've failed to disprove it so many times, I think I'm onto something. And that then continues to be tested forever. So remember, our hypothesis and our conclusions, they're not necessarily true. Now, they've been tested so many times. I'm pretty positive the stuff I'm going to be teaching you this year is true. But I can't say it is true. All I can say is through massive testing, it hasn't been proved wrong so far. So remember, you're not really proving something correct. You're just failing to disprove it many, many, many times. Now, one of the things that I want you to have a better understanding of this year, so to go beyond what you've looked at in previous years, we need to break down those parts and understand them a little bit better. First off, observation. What you're really doing in the observation phase is you're collecting data. And there's two different types of data. One would be qualitative data. That's descriptive, non-numeric information. Something like the color, the odor, the texture, saying this feels hot, this feels cold. That would be qualitative data. And remember, data is something that you are collecting using your five basic senses. The biggest one probably is sight, but you can also touch, taste, hear. All of those things are a part of it. But in the chemistry lab, we try and be really careful with touching. We try and never, ever, ever taste except under very controlled situations because some of the things we may be dealing with might be dangerous. So one of the biggest senses we rely on is our sight. So color is often a big one. People think color is a very basic property, but honestly, it's the most important thing your brain looks for in interpreting the world around you because it very quickly starts to use color to categorize what it might be. Another type of data would be quantitative data, and that's our defined numerical data, our number information. So saying the temperature is 38 degrees Celsius, the length is 24.5 meters, or the frequency is 4.1 times 10 to the 15 hertz. All those are number information, so that would be quantitative data. And honestly, whenever possible, we try and obtain quantitative data, not because it's any better, not because it's any more correct. It's just that numeric data has a level of precision to it that sometimes qualitative data doesn't have. Saying something is hot or cold is kind of a relative term. Giving a specific temperature gives us a reference point to better understand it. Saying something is hot isn't wrong, but saying what its temperature is and you realize, oh, that is very hot, is a little bit more specific. So in general, while quantitative isn't better than qualitative, it's often what we're looking for when we're collecting data. Now, second part, hypothesis, you've heard this for years and years and years. Everybody who hears hypothesis says the same thing. It's an educated guess. It's a tentative explanation or summarization of what's going on. We've made some observations, and I think this might be what's going on. One of the best ways to make sure you've written a hypothesis is to use if statements, or if then statements. So when you express your hypothesis, 100% of the time, so hint on the test and on the homework, write it as an if then statement. If this happens, then that's going to happen. So write your hypothesis in the if then form and it will help you formalize it and you're much more likely to have written a valid hypothesis. So if the weather is hot, then more people will wear shorts. That would be an example of a hypothesis. First day of school, I happen to be looking out in the hallway and I see tons of kids wearing shorts. Well, I start to think, well, maybe it's warm outside. Even though I'm in an air-conditioned room and I haven't been outside all day, I can make an educated guess about what the weather might be like outside based upon my observations that I've made. So this is my if-then statement for that situation. Now, experiment. We're going to spend a little bit more time with experiment because this gets more into the meat of things that we're going to be doing in chemistry. Now, an experiment is really a set of controlled observations. It's not random observations that we happen to notice. We set up some very specific situations and manipulate things in very specific ways to see what happens. So it is a very, very organized and controlled approach at looking at our problem and collecting new observations. Now, one of the most important parts of an experiment is what is our independent variable? Now, that's the variable that I am going to be changing as the scientist or experimenter. And in our if-then statement, this is usually what comes after the if. If I do this, then this is going to happen. So our independent variable is what the experimenter controls. The dependent variable is the variable that changes when the independent variable changes. So what happens as a result? It depends upon the independent variable. So independent, what I control. What changes as a result of that is the dependent variable. If I'm collecting data about average monthly rainfall, my independent variable is what month I'm testing. That's what I control. Okay, I'm looking at September because August is over and I already collected my August data. Now I'm controlling and looking at September data. Now, through the course of September, I end up measuring how much rain falls. That would be my dependent variable. What changes potentially as a result of what time of year it is. So that'd be an example of an independent dependent variable situation. And be careful. Sometimes in experiments, we're looking at um, a bunch of related things. We're going to end up in looking at a number of these different situations, so we will practice it. But one thing to be careful of is that you're not being too specific, because in one experiment we talked about changing this. In another experiment, we talked about changing this in this way, in a very specific way. Case in point, I'm looking at the taste of something. So I taste it without this spice and I taste it with this spice. Well, my independent variable is the type of spice I'm using or the absence of the spice. So really, I'm looking at overall a collection of those things. If I'm looking at how musical instruments sound differently, I'm not looking at one musical instrument. I'm looking at a number of musical instruments. So the violin or the clarinet or whatever isn't my independent variable. It's the type of musical instrument I'm listening to that's actually my variable. So be careful. Sometimes people hone in on, just one situation where they used one thing in an experiment and they make it too specific. So the type of instrument and how it sounds. Well, I have different types of instrument I tested, so I can't say it's the guitar. I would say it's which type of instrument I'm actually using. And then what changes as a result of that, what the sound or what the frequency ends up at, would be my dependent variable. Now, constants are really important in experiments. This is one of the reasons why it's a set of controlled observations. When we have a situation with many variables, I only want to study two, the one I change and that one that may change as a result of that. If I have other variables and I let them change, how do I know that A did this to B? Maybe B was caused by C. So what I want to do is isolate my variables and make everything else constant. So the other factors that might be involved, I want to make sure they don't change. So constants are a really important part of experimental design. You want to make sure you're only testing A and its resulting effect on B. Anything else you don't want to be changing, you want to be constant. And therefore we can rule them out as to having an effect on B. Now, control is also an important part of experiments, and it's one sometimes that students struggle with. A control is a standard used for comparison. Many, but not all, experimental situations use control. A good example of a control type situation is, let's say I'm using a chemical test to test for the presence of a certain dissolved ion. If that ion is present and I add chemical A, it turns blue. If the ion is not present when I add chemical A, it turns red. Well, before I actually test things, I want to see what those two things look like. So I'd use distilled water, which has nothing in it, and add chemical A and see what color it changes. And then I want to dissolve the specific chemical I'm targeting in the water. And then I add the chemical again in a new situation to see what the positive looks like. So I want to see a negative for unit for comparison, and I want to see what a positive looks like for comparison. That would be a good example of a control situation. So if we're testing for something, I want to see what the positive and the negative result looks like so I know when it occurs. So those are our fundamental parts of the experiment that when we look at somebody's experimental setup, those are the things you're going to have to identify. Now, an experiment is designed to test if salt will dissolve faster in hot water than in room temp water. So somebody has come up with a hypothesis, something like if water is hotter, it will dissolve salt faster. So if water is hotter, then it will dissolve salt faster. That would be an example of my hypothesis. So if water is hotter, then table salt dissolves faster. I've set it up as an if-then statement. Now, the next part of experimental design is my independent variables, my dependent variables, my constants, and my control. Now, my if-then statement can actually help me figure out my independent and dependent variables because they're in that if-then statement. Now, what I'm really doing here is testing how different temperatures of water, hot water versus room temp water, maybe even versus cold water, if I set up a more comprehensive experiment, that's what I'm specifically controlling is how hot my water is. As an experimenter, that's what I'm controlling is the water temperature. It's not room temp, it's hot. So independent variable would have to be the temperature of the water. Now dependent variable, what might be changing as a result of that? Well, in this particular experiment, I want to look at the speed with which the salt dissolves, which would be known as the rate of dissolving. How fast does it dissolve? Now constants, anything else that might affect how fast this dissolves, I want to make sure are held constant. So that way they don't have a potential effect on the dependent variable, and I can isolate every change in the dependent variable was caused by the independent variable. So things I might want to keep constant. How much salt? Maybe that has an effect on how fast the salt dissolves. So I want to always use a uniform mass of salt. How much water I have? More or less water. Maybe that affects the rate of dissolving. I want that to be constant in my experiments. How much I stir? Stirring is massively important in dissolving. Most of us just do it automatically, so you don't think about how important it is. If you take a bunch of rock salt and just carefully place it in water, it will sit there for years before it dissolves. And then take a spoon and stir it, and you can get it to dissolve in seconds to minutes. So dissolving is a very important thing that can affect rate of dissolving, or stirring has a huge impact on the rate of dissolving. So we want to make sure we stir the same way each and every single time. There's other things that might be constant, but those are a few that off the top of my head I can think of. Now, control. It's a unit for comparison. Well, in this case, I'm talking about hot water dissolving faster than room temp water. So my control really should be what room temp water situation is. So how fast to dissolve in a room temp water situation with a consistent amount of salt and a consistent amount of water and a very specific consistent type of stirring. How fast does it actually dissolve? And then I'm ready to set up my experiment and do the next part. Really test when it's hotter, does it dissolve faster? And then I could look at, make it hotter yet. Does it continue to dissolve faster? So I can really expand my experimentation from there. But that would be an example of identifying the different parts of an experiment. And there are numerous questions on the test related to those ideas. Now, finally, the conclusion part of this. Now, I'd mentioned that you might end up with a conclusion that was a theory, or you might end up with a conclusion that was a law. A theory is a tested explanation of why something occurs. So whenever you see theory, see the why, think why. Because what you're doing is actually explaining why something happens. Examples of theories. Einstein's theory of relativity, which you've all heard of, but most of you don't understand. That's a physics idea. We're not really getting into that. But things like atomic theory, kinetic theory, quantum theory, these are core theories in chemistry that we use to explain chemical situations all the time. What those things do is they explain why certain things are happening, and that's why they're a theory. Now, something that is not as important, but it does pop up from time to time, so I just want you to be aware of it, is based on the level of testing, sometimes we may have what we call a model. It's a visual, verbal, or mathematical explanation that needs more extensive testing to really move into the theory stage. So sometimes before I call something a theory, which I don't usually get the choice of whether it's going to be called a theory or not, the scientific community would, I might call it a model. So I had this model of why I think things are happening. And after extensive experimentation, eventually the scientific community agrees we have a theory. Now, law, on the other hand, is another valid type of conclusion, but it's a different type of conclusion. If we're not explaining why, we're just saying what is going to happen, then we have a law. Law ends in W, it's a what situation. So a summary of what will occur. We're not really saying why, we're just saying it is going to occur. Newton's first law, which is dealing with gravity. It's kind of the what comes up much comes down. I'm not really saying why it happens. I'm just saying if I throw something up in the air, it's going to come back down. Law of conservation of mass is a very important law in chemistry that we hit very early on in chapter 2, and we use in numerous chapters after that. So law of conservation of mass is a cornerstone law in chemistry. You can't create or destroy chemicals in ordinary chemical and physical reactions. So in that particular case, we're not saying why, we're just saying you can't create or destroy the atoms that make up substances. So your mass is going to be constant. What you weighs before is what it's going to weigh after. Now, here's an example of a scientific method problem. Homer notices that his shower is covered in a strange green slime. His friend Barney tells him that coconut juice will get rid of the green slime. Homer decides to check this out by spraying half of the shower with coconut juice. He sprays the other half of the shower with water. After 3 days of these treatments, there is no change in the appearance of the green slime on either side of the shower. So first, Homer set up an experimental situation. So first let's look at, what is his hypothesis? Well, remember we want to express this in an if-then situation. And what Homer has been led to believe is that if coconut juice is applied to the shower, then the green slime is going to be removed. So I'm taking just the general statement of what happened, coconut juice removes green slime from the showers, and putting it into an if-then statement. If I apply coconut juice, then green slime will be removed or start to disappear. What is the independent variable? Well, in this case, what am I controlling? Whether I added coconut juice or not. So the application of coconut juice or plain water would be my independent variable. What am I applying to the shower? What type of chemical am I applying to the shower? Now, what's the dependent variable? Well, it would be the amount of green slime that ends up growing. So that would be my independent and my dependent variable. So if I apply these certain types of chemicals, then what happens to the amount of slime? Now, what would be a control? Well, there's a number of different things that if Homer is careful and he really wants to study this scientifically, he needs to set up controls, he needs to set up constants. Well, a control is a unit of comparison. Well, notice he applied half with the coconut juice and he applied the other half with just plain water. So his control would be what happens if I just get it wet, the plain water. So he actually built in a control to his experiment because if he just put coconut juice on and some green slime disappeared, well, maybe that's exactly what would have happened over time or the application of water anyway. So his control in this case would be the water at half the shower. And what's the constant in the experiment? Well, things that he wants to do very reproducible. Well, he said he did it over 3 days. So time in this case was constant. Area of coverage. Maybe it makes a difference how much I'm applying. Um, the amount of liquids. So I want to use consistently the exact same amount of water and the exact same amount of coconut juice every single time. Exact same concentration because you can have more or less concentrated coconut juice. That should be the same every single time. Maybe the temperature of the liquids might have an effect. Maybe the temperature of the room might have an effect. I want to keep those things constant in my experiment to make sure I'm finding out how A affects B. The addition of coconut juice or the type of treatment and how it affects the actual production or growth of green slime. Now, last thing, in this particular case, he's done some testing here. So is the hypothesis supported by the data? And we need to justify our answer. Well, if you look at the end, he basically said after 3 days there was no change in the appearance on either side. So no, the coconut juice showed no difference in effect after 3 days. So was my hypothesis upheld? No, apparently Barney was wrong. Now, what could be done to improve this experiment? Well, there are other things that he could have held constant that he did, other things that he might have tried besides just plain water. So maybe the application of nothing might have had an effect over 3 days. So there's other things he really could have done. So he could have tried it for a longer time. He could have used higher concentration. He could have used old or new coconut juice. Maybe that made a difference. There's other things he could have done to really see if coconut juice truly was. So his simplistic experiment really left room for us to continue testing the situation. And that ends our notes on Chapter 1. Hope you have a great year in chemistry.